In this case, also think about some pullback diagram because there is some geometric meaning of the y1 tilde to the x1, y1 tilde and x1 tilde, x1. Now, we may regard this JW as an induced homomorphism from this map. Now, yes, it's on John Beck. I would like to thank John Beck. This W is one of the elements of the fixed point. And so there is this injective map because this is a fixed point. Okay? So this may be regarded as a JW. And actually, this JW star is induced from this injection. And now we've already take this kind of vector bundle. This was an equivalent vector bundle over the L rho I I've defined before. And actually, this C1, it's in the first Chern class, was a Y1 tilde, YI tilde. Okay? So let's think about this. A pullback diagram. Okay. Then this pullback diagram satisfies something like this. So I should say, now this C1 L rho I T, this defines a YI tilde. So let's recall that. And now JW star L rho I T becomes something like this. JW star L rho I T. Because of the naturality of the Chern class, this is nothing but L rho I T. And this part is in YI tilde. So this must be a JW star YI tilde. Okay? And okay, let's study this part more precisely. Now, this total space of the pullback can be written like this. Okay, this is nothing but this one. This is actually this one. This is some of the equivariant bundle over this one point. And now this W can be written by some GT because of the T over T. So let's say this W is a GT. Then this map, this pullback map, can be written by. Okay, let's remember. C rho I. So this is pullback to the only one point. So this is nothing but this kind of things. Rho I. Okay. And now actually this is by the computation. Yeah, I will omit the computation. This is nothing but this kind of vector bundle. Okay. So where? What did this mean? This W rho I. Now this rho I was an map from Tn to the S1. Yeah, actually, a while group acts on it by this way. This W rho I is defined by this. It's an rho I G inverse Tg. Okay. By this way, Wg acts on this this representation. Okay. So W dot rho I means this representation. Okay, I will omit the proof. This is just an exercise. So if you are interested, Please check it. And let's say this is an C bar W rho I. Then we see that this JW star L rho I T is an C bar W rho I. Therefore, what we know that this kind of things. Now, yes, just JW star rho ITI. Let's take the first chunk class. Of this bundle. Actually, this is by the previous computation, JW star YI tilde. And this is nothing but this part is nothing but this one. Okay. Y. Okay. And actually, this is nothing but WXI because of the definition of the W action. Because W action on the vector bundles is defined by this way. Actually, the first chunk class of this line bundle becomes Xi, and its pullback becomes, no, it's not pullback. Maybe you should say this direction. So its pullback becomes this first chunk class. So and this is WXI.
I'm sorry, could you explain the math from the right-hand side?
Right-hand side to the left-hand side?
Yeah.
This is just inverse. Sorry, this is inverse. Okay. Do you have any question? So we've done this part. This is the start part. So therefore, what can we say? Actually, in this step, we need to use a localization theorem. Therefore, what we've known is this part, JW star EY tilde is equal to EX. And moreover, this EX can be written like this. JW star composite with pi star with EX. So what does this mean? Actually, this means is obtained by this way. W is JW on the BT. Okay. Now there is an injection map by the fixed point, and there is a projection map by the fiber bundle, and then this is nothing but the identity. So this composition is just nothing but EX in this case. And recall that now we put we abuse actually this pi star x as an x, xi, as an xi. So this is nothing but an exi, ex. So therefore, jw star ey tilde is jw star ex. Yeah, actually this is satisfies for all w. Okay, so it means that from this equation we have this equation. Okay. W star ey, I should say ex, x minus ey tilde. This is equal 0. Okay, and actually this part, this is nothing but the previous one. Where's the previous one? But anyway, it's an IT star, right? Yeah, because this is an the map from this one, ht star g over t to the, actually this is an injective map to the sum of the ht star w of wg, and jw is defined by the projection onto the each coordinate, and summation on each coordinate. Then this is nothing but the it star. And now we've already proved that by the localization theorem, this it star is an injective map. So it means that this ex minus ey tilde is equal to 0. So this means that the ideal generated by this yy tilde is in the kernel of the rho. Okay? Because this is an equivalent cohomology level, and rho is a projection onto the some polynomial ring. And in the equivalent cohomology level, this polynomial is on 0. So the kernel of this rho contains this kind of polynomial. Okay. So this is done the second step. What time is it? And the third step, this is just an a tensor algebra. Now we've already obtained this kind of surjection. We've already abbreviated by this notion, and rho is induced at this surjection. And finally, in the final step, we want to prove this is a ring isomorphism. So to prove it, it is enough to prove this rho tilde is additively isomorphism. Because this is a ring surjective, if this is an additively isomorphism, then it's automatically ring isomorphism. Okay? So to prove it, this is just a tensor algebra. Maybe it's for undergraduate course students. Now, this qxy tilde, okay, I will show it quickly, over ex minus ey tilde This may be regarded as this kind of algebra, this kind of module. Now let's R be some of the a polynomial ring. Okay. Now there are two polynomial rings here, x1 to the xn and y1 to the yn. So now there is this kind of tensor. And this relation in this tensor may be regarded as this kind of relation. Tensor 1 minus 1, tensor E. Okay? And this E is a wild group invariant part. And this is nothing but, now RW is some invariant, some submodule, subring in this ring. So this is nothing but an R tensor R over RW. Okay? So this is by definition, actually. Actually, this may be regarded as an RW because E is a diagonal. And then we can split this like this. Now R is an algebra over Q. So if we put Q like this, then it doesn't change. And now this Q may be regarded as this kind of algebra. W over RW positive part. Because this positive part is taking all of the part except the constant part. So this is nothing but the Q. RW, R. And this is because of the transitive relations of the tensor product. RWR. Okay? And moreover, this part, this part may be regarded as R tensor Q. And this part is nothing but like this, written like this. The positive part. Okay? This is just an easy tensor algebra. And what is this? This was, we've already proved it. This polynomial ring is just an equivalent ordinary cohomology of the PT. And tensor, and this part is nothing but an G over T. Okay? So it means that this was additively isomorphic to equivalent cohomology of the PT, G over T. So it means that this is an additively isomorphic to HT star equivalent cohomology of G over T. So this surjection gives a ring isomorphism because this gives an additive isomorphism. So we've proved the equivalent cohomology ring of the G over T. It'll take a little bit long time. So do you have any questions so far?
Let's see. From here to there, why are...
because this is a tensor over RW. So this is quotient by, yes, RW positive.
Okay.
But this is also, yes.
Okay, that's good.
Okay, so.
This Torus original proof?
Yeah, I think so. Yeah, almost same. Okay, let's summary from this result, this proof. So in the first step, for the surjection, we use Chern classes to get a generator. So this is almost all cases we can do this kind of way to get generators. And also relation, we get localizations. To use an localization, we get this kind of relations. And in the third step, to get an isomorphism, we use just a tensor algebraic arguments. Okay, so this is a summation to prove this kind of equivariant cohomology. So in an easy case, for example, an ordinary cohomology is vanishing space, we can always use this kind of way to get an equivariant cohomology. And among this way, all of the parties and all of the steps are very important. But in particular, this part is very important. This localization theorem. Okay? Actually, to get a relation, usually in the first step, to find the equivariant cohomology, we do not know what is the relation of this cohomology algebra. So to get a relation, to find such kind of relations, this localization argument is a very important argument. And in section 4, so this is just an introduction of the GKM theory. So beyond the localization, it's a very brief introduction of the GKM theory. So by the localization, we know this kind of things. Of course, this is under some nice condition. This map is injective. This is exactly localization, by the localization. So the natural question arises. So what is this image? So if we know this image, then we almost know about ring structure of the equivariant cohomology. Okay, so the image of the very important. And this image, the GKM theory tells us what is this image. So to answer this question, the first answer is a Chan-Charbet lemma. So let M1 be a one skeleton of M. That is, M1 is defined by the set of the point whose dimension is less than or equal to 1. Okay, if this dimension is 0, then it's a fixed point. If this dimension is 1, then it's a circle. Okay, so then, actually, Chan-Charbet lemma says more strong things. But in this talk, I just use this kind of things. Then this image is nothing but the image of the this one skeleton of the equivariant cohomology. And actually this JT is an some injective map. No, this is an converse. This is an injective map of the fixed point to the one skeleton, because one skeleton contains all of the fixed point because of definition. So this Chan-Charbet lemma tells us that this image is nothing but this kind of very easiest part. Okay. And what does GChem stand for? GChem stands for the Gorensky-Kotovitz-McPherson. This theorem tells us that this JT star, so it means that it's an image of the one skeleton. Okay, we need to do some more assumption. If the dimension of the one skeleton, the orbit space of the one skeleton, is 1, so it means that this orbit space has a structure of the graph. Then the image of the one skeleton can be written by this way. This is a map from the fixed point to the actual fixed point is an isolated point in this case to some of the element of the equivalent. It's an it's a PTN which satisfies this condition. Fp minus Fq is modulo some element of the H2 secondary cohomology. So if this PQ is on ET for E is an invariant S2, and this rho E is what? Okay, I will explain it. Okay.
The name of Kotovitz?
I. You're not assuming MT is isolated.
Actually, from yes, I should assume from this dimension, from this condition, we can automatically obtain it's an isolated.
Why?
Because it's an dimension is 1.
Yeah, dimension is less than or equal to.
Yes, less than or equal to 1. So in this case, how should I say? It's an around the fixed point set. It's an okay, how should I say? Tn axon like this, and around the fixed point set, it's split into the this kind of representations. And this representation, there is no multiple representations. Then it means that its fixed point is only a 0 dimension, only a origin.
All right. Okay. Good. Yeah.
Okay. So what is this notation, and what is this E? So for example, M1 over T, this is appeared for this case. Okay, I will define it by using the by using the example. The one skeleton of the CP2 of the T2 is satisfies this condition. Okay.
So.
Yeah. Now, yes, I want to.
Before you do that,
Yes.
explain what is ET.
Yes, it is a fixed point of the PQ. And actually, I would like to explain this part.
Okay, so.
Yes.
So you. Okay, yes.
Yes. And now, in this case, there are 3 fixed points. Now, T2 acts on CP2.
Sorry?
Okay?
The Shang shared right?
Yes.
What's the condition for M?
Our condition is enough. Compact, connected, and smooth or something. Such kind of conditions.
Given M is dimensional.
Yes, that's right. In our case, it's enough. Actually, Chan-Charbet gives some more general conditions.
What is the MT, M1T? M1 quotient T is CP2?
Yes, I will.
What did you write?
I would like to explain by using the examples
CP2
now.
Parentheses, you put 1?
Yes, It means that it's a one skeleton of the CP2.
Ah, okay.
Okay?
One skeleton.
Yes. Yeah, I would like to explain it by using the example. So in this case, the one skeleton is something like this. So one skeleton admits a structure of the graph. So it means that there is an vertices, and these vertices correspond to the fixed points. And these edges, these correspond to the invariant S2. For example, in this case, this is an 1, 0, 1, like this. And actually, this corresponds to, 1, 0. Yes, Z0, Z1. For example, we will take, this is E. Then in this case, ET is an 1, 0, 0, and 0, 0, 1. Here, okay? So this condition says that between these two kind of fixed point, there is some relations, okay? And FP and FQ is actually there is some of the element of the H star PT, PTN, and this is divided by this rho E. And what is this rho E? This rho E is a representation on this sphere, okay? So rho E may be regarded as an T2 on S1. Descent. S1. Actually, this is an element of the homomorphism from T2 to the S1. And this is nothing but a cohomology of the second degree element.
So which representation? This is you have this submanifold E, right?
Yes.
So is this one manifold?
Actually, this E is an invariant S2. So it means that this is fixed by some n-1 dimensional subtorus. So then, there is this kind of natural map from Tn to the, yes.
I mean, so this is one dimensional, complex one dimensional.
Yes, complex one dimensional.
So it is representation, but what representation? So that's
it's just a restriction map to this circle action. Then it is an just this kind of homomorphism from Tn to the S1.
so this E is sort of can you express E in terms of this representation?
E?
E is just a sphere.
Yeah, E is a sphere.
Yes, in terms of this representation, okay, and
E
in
is,
this case, it's an
sphere of E plus.
This E. Okay. I'm sorry. This E is nothing but this one, this submanifold, in this case. And in this case, T1 and T2 acts on like this way, on the coordinate wise. So T1 acts on 0 is a 0. So this is a fixed point by the first coordinate of the T1. Okay, so it means that this becomes T1. So this is nothing but the projection of the second factor.
I'm a little bit confused. So can you express this sphere as a representation plus real line, circle, the hemisphere of some representation class?
Some representation class. This is nothing but a reason.
You can write the sphere as a C plus
Right.
C plus R. So
Right.
the sphere of that.
Right.
So this C has this representation structure?
Yes, of course.
Which structure? E? This is a rho E structure or?
Rho E.
So this E is S of rho E plus R.
Pardon? Say again?
E is a sphere, right?
Yes, that's right.
So is this E same as S parentheses rho E plus R?
S of rho E plus R.
Yeah, rho E is a complex one-dimensional representation. No?
In usual, rho E may be regarded as a complex space. Yes, that's right. Yes. Yes, you are right. So, so strictly speaking, maybe you should say C rho E, something like this.
Yeah.
Okay, so what I want to say is, so from this GChem theory, so beyond the localization, so in this case, this kind of graph appears. So to compute the equivalent cohomology, we can use the combinatorial structure of the graph. So this is a GChem theory, and this is a recently active area. So if you are interested, please ask me later. So maybe it's a time, I think. So I'll stop here.